Lastly, we have to introduce Poissons Ratio. Now, recall the conservation of mass. The mass of our material must be conserved. That is, when a material is loaded axially, we're going to generate strains in the radial direction, perpendicular to our direction of loading. That is, as we begin to elongate a material under tensile loading, our cross-sectional area has to decrease for us to conserve mass. Conversely, as we begin to compress a material, as our length decreases, our cross-sectional area must increase. We can relate our transverse to our axial strain via Poissons Ratio, where nu is equal to the negative of our transverse strain per our axial strain. Now, this relation is only valid for uniaxial loading. Nu is a material property. It exists between 0.27 and 0.30 for steels and around 0.32 for aluminum. And we can use Poissons Ratio to relate our elastic modulus to our shear modulus. That is, our modulus of elasticity E is equal to 2 times the quantity 1 plus nu times our shear modulus. We can see an example of Poissons Ratio. Let's consider a 16.0 millimeter diameter rod that has a length of 500 millimeters. This rod experiences a load of 12.0 kilonewtons. If our deformation in our axial direction is 300 micrometers and our diameter decreases by 2.40 micrometers, we want to determine our modulus of elasticity in Poissons Ratio for this rod. To do such, we first have to calculate our average normal stress. Our average normal stress is equal to our internal reactionary force per our cross-sectional area. And this would be equal to 12.0 kilonewtons per pi times our diameter, which is 0.0160 meters squared per 4. And our average normal stress is going to be 59.7 megapascals. Next, we have to calculate our average axial strain, which is our deformation in our axial direction per our original length, where we'd have 300 micrometers per 0.500 meters. And our average axial strain is 600 mu. Now, our modulus of elasticity is found via our stress-strain relationship. E is equal to our average normal stress per our average axial strain, which is equal to 59.7 megapascal per 600 mu. And this is equal to 99.5 gigapascal. The average transverse strain is found as our deformation in our transverse direction per the characteristic length describing this direction. In this situation, delta is equal to minus 2.40 micrometers, for our diameter has decreased. L in this situation is not the length of the bar. It is a characteristic length in our transverse direction, i.e. our diameter. So we'll take this value to be 0.0160 meters. And we find our transverse strain to be minus 150 mu. Thus, we can find Poissons Ratio as a negative of our transverse strain per our axial strain. We'd have the negative of minus 150 mu per 600 mu. And nu we find to be 0.250.